Okay, let's get started. Hopefully you have already finished the homework 8, because it was super easy. If not, get started on it and do it. Get it done, get it out of the way. Because it's due on Tuesday, and you want to save time and make time for studying for the exam, right? So if you remember homework 6, homework 7, there's a lot of really big stuff on there. It's nothing that you haven't done before, but some of these problems can be very involved and very complicated. My intention on the exam is to have one big, involved, complicated problem and then several smaller problems. So there will be one kind of system problem that you have to work out, and there may be exergy involved, there may be mass flow rates you have to calculate, there are a lot of different things that I can put in there. So make sure that you understand the basic fundamental concepts of how to approach problems. Because there won't be anything you haven't seen before. You just may not recognize it because you get overwhelmed by looking at the picture of the system. Okay. So as you're studying, please be very mindful of that, going back to basics, making sure you understand how to approach a problem, how to analyze it from the ground up, and not get too overwhelmed with the information that you're given in the problem. Okay, so our exam's a week from today. We'll review on Tuesday. We'll have a review session where we can do some problems. If you have particular things that you want me to cover, send me an email and let me know, and I'll make sure to include those in the review that we do. So if there's some topics that you're struggling with, or problems that you want to see done or see again, send me an email. Don't send me an email on Monday night at midnight. Send it over the weekend or sometime so I have time to prepare and answer your questions. Because today we're moving on to chapter 13. This will be included on the exam, but just very basic measure of it. Chapter 13 is what we will build upon as we start looking at internal combustion engines and mixtures of gases now operating in systems. So although we won't go into great depth on the exam with the topics from chapter 13, it is still information you need to learn, because what we do after the exam will be based upon what we learned in this chapter. So don't just write it off and ignore it. So up until now we've looked at gases that were by and large just a single substance. Now air is a mixture of nitrogen and oxygen and a bunch of other things, but we just call it air, and we just treat it as a simple ideal gas. Well, now we're starting to look at what happens when we have mixtures of gases or mixtures of different working fluids within the same system. How do we analyze those? How do we determine property values? How do we do energy analysis? How do we determine what's happening in the system when we have fluids with different properties? And when I say fluid, that's just a generic term for anything flowing through a system. It can be in the gaseous form or in the liquid form. Today we're talking about how to deal with gases of different varying properties. And so in order to determine how our system functions or what happens to this combination of gases within the system, we need to know a few things about it. We need to know the ratios of how much of a certain substance are in there, or perhaps we know the mass of each of those individual components. We need to know a little bit of information. We can't just take unknown gases and figure out necessarily what's happening. We need to know a little bit. But we can look at it in two different ways. We can look at it on the molar basis, so looking at the number of moles of each particular substance, and we find kind of like a conglomerate average. Or we can look at it on the mass basis. So these two different types of analysis. The first is a molar analysis, where we're using the number of moles of each substance. And the gravimetric analysis, where we're using the actual mass of the substance to determine how the overall whole gas operates. So we're going to look at and learn these two different methodologies today. There's a lot of terms that go along with this, and they have subscripts associated with them. Very, very important for you to keep track of the subscripts, because whether you're looking at the mass of the individual or the mass of the whole, or if you're looking at the mass fraction of the individual, you need to make sure that you understand what M refers to, and whether it's a capital M or a lowercase m. Okay, so there will be a lot of that. Be very careful with your subscripts and keeping track. So here are a few of the components that we're looking at in order to determine how these gas composites are put together. This M sub M is the mass of a mixture. Okay, so it would be the total mass of whatever substance we are studying. And it's going to be a sum of the individual masses of each component. So this I means individual, whereas mass, or the M, means mixture. So mixture is M, individual is subscript I. And that will be the standard notation throughout this whole chapter. Similarly, we can look at it on a molar basis, where the number of moles is equal to the sum of the number of the moles of each individual substance within the mixture. So there's a total mass, there's a total number of moles. Then we can look at the mass fraction. So the mass fraction is the ratio of the mass of some individual component divided by the total mass of a mixture. Similarly, the mole fraction is the individual number of moles of each individual substance divided by the mole number of the mixture. So these values, this M sub M and N sub M, are going to be the same or consistent throughout for any given problem. Okay, that's not going to change. What is different is this M sub I, N sub I, and then the mass fraction and the mole fraction. So those will be given for each fluid that you have in your mixture. So if you have a mixture of 27 fluids, guess how many times you have to calculate the mass fraction? 27 times, right? So if there's 4, you calculate it 4 times. If there's 2, you have 2 different ones. So depending upon the number of components to your system, this may be a very big and involved problem, or it might be a little bit smaller and easier. We're going to do some examples today that have 2 and 4 and a couple of different numbers. Okay, so we can also look at alternate ways of expressing masses and molar masses and mass fractions. And so this slide gives you an idea of how all of these different quantities are related one to another. So the mass of a mixture is equal to the number of moles of the mixture multiplied by the molar mass. And if you go to table A1 in your book, up until now we haven't used the molar mass very often. There have been a few problems where we had to convert. But table A1 gives us a lot of information that we will need to solve all the problems in this chapter. So if you look, there's a big capital M that has molar mass, and the units on that are units of mass per mole. So it's kilograms per kilomole is the unit on a molar mass. Yes?
Which table?
A1, very first table. So there's the molar mass, there's a gas constant because every substance has a slightly different gas constant. We also have the critical point, temperature, pressure, and volume, and we'll use those today as well. So very important, table A1, all of the molar masses are in here. You'll also notice, for example, ethane. What's the molar mass of ethane?
.07.
Okay, it's 30.07. Very commonly, that's approximated as 30. Okay, so if you want to do that in your problems, that's totally fine with me. The same for some of these others, like nitrogen is 44.013. If you want to just call it 44, that's okay too. So know where to find those and know that there's a lot of gases in here that we haven't even considered up until now. Okay, so the mass is equal to the number of moles times the molar mass, and for a mixture, it's going to be the mass of the mixture divided by the number of moles in the mixture. So if you remember from previously, we determined that we can sum up the number of moles and the number of, and the mass of each individual component. So this mass of the mixture is also equal to the sum of each individual component of the mixture, which we could also rewrite that it's the sum of the number of moles of each individual times the molar mass of that individual substance as well. So there's a lot of different ways to find the same answer. Part of it depends on what you're given in the problem, because sometimes you'll be given a molar values. You'll say, you have this many moles of this and this and this. Sometimes you're given kilograms. Sometimes you're given volume percents or mass percents. So you need to know how to convert between all of these different systems. So if you have mass, how do you find molar mass? If you have moles? How do you find mass? So knowing how to do that is critical and important. And if you forget the equation, how could you, aside from looking up the equation, how could you do that? How could you figure out what multiplies by what?
Units.
Units. You look at the units, right? So if you're trying to get kilomoles and you have something that's kilograms per kilomole and something else that's kilograms, right? You can figure out how to do that in order to get kilomoles back out. Okay, similarly, we can find a lump average gas constant for our system. So it will be this universal gas constant, which is in SI units 8.31447 kilojoules per kilomole Kelvin. And then you divide through by the molar mass. Okay, so this is like finding the gas constant of this mixture. You're dividing through by the molar mass of the mixture using the universal gas constant. And then mass fractions can be determined in a similar way. So if you know the mass of each individual, divide through by the mass of the total, or you can do it using moles and molar mass. And then of course, this mole fraction is Ni over N sub M. So all of these terms can be manipulated and used and changed, and depending on what you're given initially. Okay, so sometimes you need to find the mass fraction, sometimes you're given it. So let's do an example where we have a mixture consisting of O2, N2, and CO2. So we have three gases. We need to determine the mass fraction of each component. So how many mass fractions will we need to calculate? 3. And how many mole fractions will we need to calculate? 3. And the average molar mass and the gas constant of the mixture. So the average molar mass, how many of those is there? Just one. And then there's just one gas constant for the mixture. Okay, so these mole fractions and mass fractions are for each individual component, whereas the molar mass, the average molar mass and the gas constant of the mixture is for the whole thing itself. So we go to table A1 and we start looking stuff up, right? Because we need to know for O2, the molar mass is 31.9999 or 32 kilograms per kilomole. And R is 0.2598 kilojoules per kilogram Kelvin. For nitrogen, our molar mass, and if you want to put little subscripts on these so you keep them straight, that's helpful too. I like to make a little table. That helps me keep things organized. Kilograms per kilomole, so it's 28.013 or just 28. R is equal to 0.2968 kilojoules per kilogram Kelvin. And for CO2, our molar mass is equal to 44, and our R value is equal to 0.1889 kilojoules per kilogram Kelvin. Okay, so we're told we have 2 kilograms of oxygen, 5 kilograms of nitrogen, and 7 kilograms of O2. How do we find a mole fraction? Or mass fraction, that's the first one. How do we find a mass fraction?
Molar mass minus like over the number, the amount of mass.
So the mass fraction is equal
to the individual over the mass of the mixture.
Right, is equal to the mass of the individual over the mass of the mixture. So for each one of these, we know we have 2 kilograms of O2, right? So the mass fraction of O2 is going to be equal to 2 kilograms over what? 14 kilograms, right? Because that's the total mass of the mixture. We just add 2 plus 5 plus 7, we get 14. So the total mass of the mixture is equal to 14 kilograms. So we can find the mass fraction of O2, the mass fraction of nitrogen is equal to what? 5 kilograms over 14 kilograms. and the mass fraction of CO2 is equal to 7 kilograms over 14 kilograms, right? So these values are 0.143. And notice these are unitless, right? Because it's kilograms divided by kilograms. 0.357 and 0.5. And if we want to be thorough and do a double check, we could add these up. 0.143, 0.357, and 0.5 should add up to 1. Those mass fractions, the sum of which should all be 1. Okay, pretty easy, right? Easy stuff. We're just doing some math here. So now we need to find the mole fraction. What is the mole fraction?
Individual mole of the total.
Okay, so Y sub I is equal to the number of moles of the individual over the number of moles of the mixture. Do we know the number of moles of individual? What is it? It's this n value. Do you see anything that's an n? No, we don't know the number of moles. We know the mass, right? And we know the molar mass. Moles are in the units of kilomoles. How do we get kilomoles with what we already have? Yeah, so N is equal to mass divided by molar mass, right? So we have kilograms over kilograms per kilomole. Kilograms cancel out, and then we're left with kilomoles. So we can find the N values for each of these using the mass, 2 kilograms divided by the molar mass. So 2 over 32 gives us 0.625 kilomoles. 5 over 28 gives us 0.178 kilomoles. And 7 over 44 gives us 0.159 kilomoles. So now we know the mass of each individual, the number of moles of each individual, we know the mass, or the molar mass of each individual. What we're trying to look and find out is the mass fraction, or molar fractions. Yes?
The ends, is that the same way? Should they add up to 1 or no?
No. Then,
That's just its own thing.
no. The molar fractions will add up to 1, but the ends are just a number. So it's like adding up masses.
Oh, okay.
Yeah, so, but now we find our molar fraction, our molar fractions, which are equal to this N value divided by the total N of the mixture. So if we add up all of these moles, the mass, or the molar number of the mixture will be equal to 0.3995 kilomoles. So then we find our molar fractions by dividing this 0.625 over 0.3995 and 0.178 over 0.3995 and 0.159 over 0.3995. So that's our molar fractions for each individual substance.
So how's it 0.3995? Is that just,
0.0, sorry, it's a 0. 0.065. Good catch, because that wouldn't have added up otherwise. Yeah, because it's 2 divided by 32 gives you 0.06. So once we determine these molar fractions, so in this case it's 0.156, 0.446, and 0.398. Okay, so that's part B. And if we were to add those up, 0.156, 0.446, 0.398, it should be equal to 1. Okay, now the average molar mass. The average molar mass is just going to be equal to the mass of the mixture divided by the number of moles of the mixture. So the mass of the mixture is 14 kilograms, the number of moles is 0.3995 kilomoles. So we find this to be 35.04 kilograms per kilomole. And then similarly, our R value of the mixture is equal to the universal gas constant divided by the molar mass of the mixture, which we just solved for. So it's 8.31447 kilojoules per kilomole Kelvin divided by 35.04 kilograms per kilomole, blah, blah, blah. Gives us 0.237 kilojoules per kilogram Kelvin. And this is another point where you would do a reality check that this number should be on the order of between 0.1 and 0.8 usually. So looking at your gases, you see like the R values for these 2.25, 0.29, 0.18, 0.237 seems reasonable. Okay, so if you start getting really crazy, wacky numbers like 1.5, or you need to go back and see what you've done wrong. So all throughout this process, you should just be double checking, making sure that you're doing it correctly, making sure your mass fractions add to 1, making sure your mole fractions add to 1, and that your answers are reasonable, because it should be somewhere in between your highest and lowest molar mass, or your highest and lowest gas constant, right? Because it's averaging them all together. If you get higher or lower, then you've done something incorrect. Okay, so, yes.
You have Rm equals R4.
RU, the universal
RU.
gas constant,
Okay, sorry.
R sub U.
And that's 0.31447, right? Or 8.
8.
Okay.
And that's at the bottom of the table here,
Gotcha.
table A1, so it's in there. And if you're working in English units, then you go to table A1 English, and that information is there. When you're working in English units, you have to be careful though, because sometimes you're working in BTUs per pound mass, and sometimes you're working in PSIA per feet cubed, so make sure you know how to convert. Okay, so we know kind of how to find this mass average, mole average, to determine like our molar mass or our gas constant, but we need now to understand how these gases behave when they start mixing together. Because if they're operating as an ideal gas, it's fairly straightforward. If it's a non-ideal gas, then we have to do some other tricks and figure out what's going on. So when it's the ideal gases mixing together, they continue to behave like an ideal gas, and it's easy. But if we have these non-ideal gases, we sometimes have to use two different laws, Dalton's law or Amagat's law, in order to find a better approximation for the behavior. If you're mixing an ideal gas with a non-ideal gas, or if you're mixing more than one non-ideal gas together, that the way that the molecules interact at different pressures sometimes causes interesting problems. So Dalton's law of additive pressure says that the pressure of a gas mixture is equal to the sum of the pressures of each gas. So if we have a gas A and a gas B, gas A is at pressure A, gas B is at pressure B, then we say that this gas mixture is going to have a pressure that's equal to pressure A plus pressure B. And this is exact for ideal gases. So if it's an ideal gas, this always holds true, and it's approximation for real gases. So when we look at this, P sub I, again, is the individual component pressure, and we can also come up with something called the pressure fraction, P sub I over P sub M, which is analogous or similar to a mass fraction or to mole fraction, where we're finding this other ratio that sometimes we use to determine other things. Amagat's law of additive volume says that instead of adding the gases together and looking at the pressure change, we're now adding them and looking at the volume. And so we say that volume instead is cumulative rather than pressure. So it's equal to the sum of the volumes of each gas if they existed alone at the temperature and pressure of the mixture. So if these gases are coming together at the same temperature and pressure, then it's easy to determine the final temperature and the final temperature of the final temperature and pressure of the mixture. But if they're coming in at different temperatures and different pressures, then you often have to determine, using ideal gas law and corrections, what the actual temperature and pressure will be. But we say that it's just a combination of volumes if these gases were at the temperature and pressure of the mixture. Yes?
So, I'm having trouble wrapping my mind around combining the pressures. I guess I think they would find like a homeostatic point between the pressures, like an average pressure, instead of combining.
So what it's saying is that it's not necessarily that this gas is coming in at pressure A and pressure B. It's that if we were to look at this gas mixture that has some final volume and temperature, and we were to presume that our gas A is existing at that volume and temperature, and gas B is also existing at that volume and temperature, even though they may come in at some different value, then we can say the pressure that gas A would exert if it were at that volume and temperature, and the pressure that gas B would exert if it were at the volume and temperature, we add those together.
Okay.
Yeah, so you're right. So if there's some high pressure gas and a low pressure gas, it's not like they're going to add and it's going to be higher pressure gas. But we make this assumption that these gases are coming in at the same volume and temperature as this final mixture, and that their pressures will be additive in that case. And then in the law of additive volumes, it's saying that if it were at the pressure and temperature of this final mixture, that we could just add the volumes together. And this is another way of, it's almost analogous to when we were doing the partial derivatives and we were holding something constant. So here we're saying, okay, pressure and temperature are constant, and then the volumes are being changed or added together. So it's one way to eliminate one of the unknowns. So if you have pressure and temperature and volume that you were juggling and trying to figure out, it's significantly more complicated. But if you say one of those we can know based on the other two, then it makes it a little easier. Okay, any other questions on that? When we see it in practice, it's a little bit easier. Okay, so now we know that for an ideal gas that it's equal to PV is equal to MRT, or P lowercase v is equal to RT. But we can also write it in this way, where PV is equal to the number of moles times the universal gas constant times T. So it's the same expression of what we've used before, but now this is the molar form. So what we can say is if we have some individual gas that's at this individual pressure and a temperature of the mixture, volume of the mixture, we divide through by the pressure of the mixture. This is an equivalent way of expressing this molar fraction. So this is like looking at it from Dalton's law perspective, and this is like looking at it from the Amagat's law perspective. So what we're saying is that this individual pressure divided by the pressure of the mixture ends up being equal to the volume fraction, which is equal to the molar fraction, y sub I. So allowing us to apply these two laws, Amagat's law and Dalton's law, gives us another tool for calculating basically the molar fraction of the mixture. Okay. Let's do an example. And in this case, we have, and this example probably should be before we start talking about Amagat and Dalton's law, because we don't fully use them, but anyway. We have a rigid tank that has nitrogen, and it's connected to another rigid tank that has oxygen in it. Okay, so there's a valve in between, and right now they're separate gases. The valve is closed, but then we're going to open the valve and allow them to mix. So there's 2 kilograms of nitrogen, and it's at 25 Celsius, which we could go ahead and convert that to Kelvin. It's 298 Kelvin, right? And 50 kilopascals. And then the oxygen, there's 4 kilograms of that, and it's also at 298 Kelvin, and there's 150 kilopascals is the pressure. So the gases are allowed to mix, and we're assuming the final temperature is the same as the individual temperatures in the beginning. So we want to figure out the final volume, and then, or determine the volume of each of the tanks and the final mixture pressure. Okay, so we look up some characteristics of oxygen. We have M is equal to 32 kilograms per kilomole. For nitrogen, we have M is equal to 28 kilograms per kilomole. And our R value for oxygen is 0.2598 kilojoules per kilogram Kelvin. And the R value for nitrogen is 0.2968 kilojoules per kilogram Kelvin. Okay, so to determine the volume of each tank, right now we have an ideal gas in one tank and an ideal gas in the other tank. It's fairly easy and straightforward. So the volume of the oxygen, we're going to assume that the oxygen comprises the entire volume of the tank, that is filling the entire space. The volume of the oxygen is equal to the mass of the oxygen times the R of the oxygen times the temperature of the oxygen divided by the pressure of the oxygen. Okay, so we're given the mass, we looked up the R, we have the T and the P, so we can calculate that volume as 2.065 meters cubed. We do the same thing for the volume of the nitrogen, or is this MRT over P. All of these are nitrogen values, and we find that it's 0.322 meters cubed. Okay, so while they are separate and distinct, it's very easy to calculate their volume.
Is that a capital M or a lowercase m?
Lowercase m. Okay, so we've just calculated the volume of each of those. So now we want to calculate some of the other things. The first is the mole number. So the mole number of oxygen is equal to the mass of oxygen divided by the molar mass of oxygen. So that's 4 kilograms divided by 32 kilograms per kilomole, which is 0.125 kilomoles. And we find that the molar number of nitrogen is equal to the mass of the nitrogen divided by the molar mass of the nitrogen, and that is 0.0714 kilomoles. That's hard to read, sorry. 0.0714 kilomoles. Read that.
Is it a 0?
It's a 0. It's a potato. 0.0714 kilomoles. So then we find the N of the mixture is equal to this plus this is 0.1964 kilomoles. So now to determine the pressure of the final mixture, we're again applying the ideal gas law, but this time we're using the molar number of the mixture, the gas constant, the temperature of the mixture, and the volume of the mixture. So to find the final pressure of the mixture, we plug in all of those numbers, we find that it's 203.85 kilopascals.
And you just use the volume of those two added together, right?
Yes, but the volumes were additive. Yes.
Were the temperatures added together and there are values?
No, the temperature of the mixture is 25, it's given in the problem, so it's 298 Kelvin. But the volumes, so volume of the mixture is equal to the volume of O2 plus the volume of nitrogen. So it's 203.85 kilopascals. Yes,
What's the
R sub U It's 8.31447 kilojoules per kilomole Kelvin. It's the universal gas constant. So anytime you're using the ideal gas equation where you have PV is equal to nRT, this is always the universal gas constant. Because N is in units of kilomoles, and the universal gas constant is in kilojoules per kilomole Kelvin. So if you're using the ideal gas equation in the molar form, you have to use the ideal, the constant, the universal gas constant. Okay. Because R is equal to R sub U over M for every gas. So this universal gas constant is universal, and then we find our R values by just dividing through by the molar mass of each individual gas. So, but that's already been tabulated for us. Okay, so real gas mixtures, we can approach this similar to how we found property values for real gases back in chapter whatever, using the compressibility chart, A15 I believe it is, where we need to find a Z value by using the critical point properties of the gas in order to look it up. But the way that we do it when we have a mixture of gases is that we find the Z value for each individual component, and then we add them together using the molar fractions. Okay, so you can see how these problems can get to be very big. Like this next example takes 2 pages, and it's just because it's dumb little teeny calculations. It's nothing difficult, it's just a lot of calculating molar fractions of Z's and things. Yes?
So the two laws that you just showed us, like adding the pressures and adding the volumes, those were just for ideal gases, or that you can use those for real gases too?
They are approximate for real gases. So if your real gases are close to behaving like an ideal gas, they're a pretty good estimate too. But what we're doing now is we're saying, okay, we can, it's similar to what we did in chapter 12, we can analyze this as if it were an ideal gas, and then we're going to add on a correction factor.
So like it'd be like almost like a comparison problem. Like,
Yes.
Okay, that's why I was like trying to figure out if like one way is better than the other, but like you compare the answers, like assuming that it's an ideal.
Right.
And then the actual.
Right, and then you see how much percent different it is, because in some cases it may be almost the same value. If you're far away from the critical point, then usually it's a good indicator that it'll be better received if you would use it as an ideal gas. Okay, so we can use these laws of additive pressure, laws of additive volumes, but we have to use the correction factor in our equation. So now we just add in this Z value. So we treat it as an ideal gas, we look up the information in the tables, we do the analysis as if it were an ideal gas, and we come up with some final value. And then we put in the correction factor using its actual temperatures comparing to the critical point. Okay, so we'll go through some examples of that where you can see how that works. And there's the question of, well, which one do I use, Amagat's law or Dalton's law? It turns out that at higher pressures, Amagat's law is a better fit, and Dalton's law is more accurate at lower pressures. So ideal gases are often at low pressures, so usually if you're using Dalton's law for an ideal gas, you're good. If you're working with real gases, generally they're at higher pressures, so sometimes you have to work with Amagat's law. So it just kind of depends on what you're given initially, which one is best to use.
How do we know, like, what the pressure is that we would switch on? Is there like a good number?
No, and it will vary for every gas. But if you are just looking at your critical point pressures, so in this table, A1, you can also see, like, for ammonia, it's 11.28 megapascals.
Mhm.
But for helium, it's 0.23 megapascals. So you can see how if you're operating with ammonia, you're going to have to be at a very, 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 very high pressure to be far away from that critical point. So, I mean, it just kind of, you kind of have to play with it. And then, in any case, you can always treat it as an ideal gas, figure out what your Z value is and see how far off you were. Okay, so another rule that we can use, it's an alternate way of doing it. So rather than calculating the Z value for every single individual component, we now say, okay, I'm just going to average all of their critical points together and find an average critical point temperature and an average critical point pressure, and I'm going to use that to calculate the Z value and have some average critical point Z value. So this is called a pseudo-critical point. It's where you're just taking sort of like the lump average of all of the critical points of these individual gases, and you're finding where on the map approximately you would be. And you're using the molar fraction, because if you have a larger quantity of a certain gas, it's going to have a greater influence on how far away from that critical point you place it, right? So it has a greater weight when determining where to find that average pseudo-critical point. Yes, you guys will love this, I can tell. And we'll do an example with that, so it makes more sense. I don't know where my time is right now. Okay, we've got time. Okay, so this is a big example. Get out a big, nice, empty sheet of paper. It is 2 pages. And I'm going to add another slide. Okay. So we have a mixture of gases. It's oxygen, nitrogen, carbon dioxide, and methane. So we have this mixture of gases, and it flows through a pipe at 8,000 kilopascals and 15 Celsius with a velocity of 5 meters per second. So we have to determine the volumetric flow rate and the mass flow rate of the mixture first, treating it as an ideal gas. Second, using a compressibility factor based on Dalton's law, and then third, using K's pseudo-critical pressure and temperature. So this will be really fun. First thing we need to do is go to table A1 and start looking stuff up. So we're going to need the molar mass, gas constant, the critical point temperature, and the critical point pressure for each of these substances. So if we have CO2, O2, nitrogen, and methane, which is CH4. So I'll just put these values in. 44, you can see how hiding a table is handy. 28, 16, and the units on these are all kilomole, kilograms per kilomole. R value is 0.1889, 0.2598, 0.2968, and 0.5182. Critical point 304.2, 154.8, 126.2, and 191.1. And then our critical pressure 7.39. This is all in Kelvin. This is all in megapascals. 7.39, 5.08. Hopefully you can read that. 3.39. 4.64. And this is, of course, in kilojoules per kilogram. Okay, so we've looked all of those up, and we're told a percentage by volume. So we're going to assume that our volume is based on 100 kilomoles. So a volume percentage and a molar percentage are going to be equivalent. So we're going to assume that we have 30 kilomoles of O2, 40 kilomoles of N2, 10 kilomoles of CO2, and 20 kilomoles of methane.
So you said we're just assuming it's based off 100?
Yeah, it doesn't matter because it ends up canceling out later anyway.
Okay.
So we can just choose any arbitrary value for that we have 100 kilomoles of this substance, and then it doesn't matter what it is because it cancels out.
That's any number will cancel out?
Yeah,
Okay.
yeah. any number you choose for this, but choosing 100
It's easy.
is easy because it's percentages, right? Okay, so we need to go through and figure out our masses. So the mass of each of these is going to be equal to the number of kilomoles multiplied by the molar mass. So I'm just going to write it up here just so I have it in my same table that we're figuring out the mass of each of these also. Ugh, sorry. I'm not driving very straight today. Okay. So if we do this calculation where we're using kilomoles, then we have this is for 40 kilograms. Oh, wait a minute. Okay. So there's another line up here. Okay. So 440 is for the CO2, 440 kilograms, 960 kilograms, 1120 kilograms, and 320 kilograms. Okay, so for each one of those, I multiply the molar number, which is just 30, 40, 10, 20, whatever it is, times this molar mass. Okay, so then I can determine the mass of the mixture is going to be equal to the sum of all of these. So it's 2840 kilograms. And then the molar mass of the mixture is going to be equal to this molar mass divided by the number of moles. So it's 2840 divided by 100 kilomoles. That was what we assumed in the beginning. It's just 28.4 kilograms per kilomole. So this is the number that's important, the molar mass of the mixture, and that's why it doesn't matter what we choose for the 100. Because if we chose 30, then this would have been some value that's whatever, and then we divide through by 30, and it just we'd get the exact same answer. Okay, so in part A, we just treat it as an ideal gas, which means that if we're solving for volumetric flow rate, it's going to be equal to A times the velocity. That's independent of the properties at all. Mass flow rate is going to be equal to this volumetric flow rate divided by specific volume. So we need to determine the specific volume in each case, A, B, and C. And if it's an ideal gas, then the specific volume is just equal to RT over P, right? But it's the specific volume of our mixture, so we need to find an R of the mixture, and then T of the mixture, and P of the mixture are given, right? So the mixture flows at 15 Celsius and 8,000 kilopascals. Those are given, but we need to find this average R. So this average R, or the R of the mixture, is going to be equal to the universal gas constant divided by the molar mass of the mixture. So we calculated that already. That's the 28.4. Universal gas constant is fixed, 8.31447 kilojoules per kilogram Kelvin. No, kilomoles Kelvin divided by 28.4 kilomoles. So we find our R, our gas constant, is equal to 0.2927 kilojoules per kilogram Kelvin. So we look again at our table and we say, okay, 0.1889, 0.2598, 0.2968, 0.5782, 0.29 seems reasonable. It's kind of in the middle of those values, right? So now we can calculate our V sub m. And if we plug in the numbers for that using the gas constant that we just calculated, our temperature is 288 K. And our pressure is 8,000 kilopascals, then we get a volume equal to 0.01054 meters cubed per kilogram. So that's the specific volume of the mixture. We could also, if we wanted, determine the individual specific volumes of each gas. We don't need this. And then we could find the, yeah, we don't need that. Okay. So now we can just calculate, calculate our volumetric flow rate, which is equal to pi d squared over 4 times the velocity, which is, everything is given to us in the problem. We find that is equal to 0.001005 meters per second. And then our mass flow rate is equal to V dot over V. So this 0.001005 divided by 0.01054. We find that it's equal to 0.09535 kilograms per second. Okay, so treating it as an ideal gas, we found the volumetric flow rate, which actually won't change at all for any of the cases, and the mass flow rate. Any questions on that? Okay, so basically what we needed to do was find this lump average gas constant in order to calculate this average specific volume of the full mass of the mixture. Okay, so now what we're going to do is use the Dalton's law and a compressibility factor. Okay. So we need to find the reduced temperature and pressure for each of our substances. So for CO2, the pressure for CO2, the reduced temperature for O2, the reduced pressure for O2, for nitrogen, and for methane. So for each of these, the reduced temperature is going to be the temperature over the critical point temperature, and the pressure over the critical point pressure. So this critical point temperature and critical point pressure changes for every substance, right? So we looked those up in the table. This T sub CR and P sub CR is different for every substance, but this T and this P is the same for each one. So T is going to be equal to 288, P is going to be equal to 8 megapascals, but then the critical point, we have to look in the table and find each individual one. So doing all the math on that, I'll just give you the reduced values. So for, let's see, that's over 304.2. This one is over 7.3. So we have a 0.947, 1.083, 1.86, 1.57, 2.28, 2.36, 1.51, and 1.72. Okay, so now using these values, we go to table A15 and we find an approximate Z. So this one is about 0.95. This one is about 0.85. This one is about 1, and then this one is about 0.2. Okay, so 0.2, 0.95, 1, and 0.85. So now we say, okay, we're going to figure out, using that together, what is our average Z value. So we use, again, the molar fractions, which are based on those percentages that we had earlier. So 0.1 times the Z value of 0.2 plus 0.3 times the Z value of 0.95 plus 0.4 times the Z value of 1 plus 0.2 times the Z value of 0.85. So we find this average Z value for the mixture is 0.875. So now we use that back in our ideal gas equation where PV is equal to ZRT, V is equal to ZRT over P. So essentially what we're doing now is we're calculating this V that we calculated before, the RT over P, here, right? Using the same thing, R of the mixture, T of the mixture, P of the mixture, but now we're multiplying it by that Z factor. So then we calculate that value to be 0.00922 meters cubed per kilogram. Our V dot stays the same because it's only based on velocity and the diameter of the pipe, so 0.001005 meters cubed per second. But our M dot now changes to be 0.109 kilograms per second. Whereas before it was
0.0.
0.09, now it's 0.109. Okay, so it's increased a little bit using this new method. It doesn't like me switching back and forth. Okay, so that's using the compressibility factor and Dalton's law.
Dalton's always that second part, right?
No, this is the compressibility factor. Dalton's law allows us to assume that we can use these temperature and pressure to find some like conglomerate temperature and pressure.
Okay.
Okay, so now we're going to use K's rule, which is a little bit easier because we don't have to look up quite so many Z values. Instead, we find T critical, which is equal to the sum of all of the T criticals of each individual multiplied by the mass fraction of each individual. So again, looking up in the tables, finding those values, multiplying it by the mass fraction, which is those percentages, and we find 165.56 Kelvin for our T critical, and our P critical is now 4.547 megapascals. So then you can look at these values and you can compare them to your to all the ones for your individual properties. It should be in between the highest and the lowest. Make sure that you've done that right. So we find a reduced temperature, which is the temperature of the mixture divided by this new T critical, and a reduced pressure, which is the pressure of the mixture divided by this P critical. And we find that to be 1.74. This one is 1.76, which gives us a Z value of approximately 0.9. So then we do the exact same thing that we did before, but now our Z value is 0.9 instead of 0.95. So we can calculate a new mass flow rate, and the value that we get this time is 0.1081 kilograms per second. And our specific volume ends up being 0.0093 meters cubed per kilogram. Okay, so these are all iterations of the same basic concept. One is that you're just assuming it's an ideal gas. The second is that you're assuming it's not an ideal gas and you're finding a correction factor for each point in the graph, and then finding this average Z value. And then the third way is that you're finding an alternate or a pseudo-critical point and using that to calculate your Z value. And so you get different answers. This 0.95 is different from this 0.9. And I can't say specifically which one of those two methods is more accurate. One may be better than the other. We would have to do some experiments on the actual mixture to figure out which one is more accurate. Okay, any other questions on this? So these problems are time intensive just because there's a lot of little calculations to make for each gas, but they're not difficult. And as long as you're being careful and you're making sure that after each step you do a reality check, make sure that it's a sensible answer, that you haven't misplaced a decimal or something like that, then you'll be fine. Okay, so when we start looking at the property values now of these gas mixtures, one thing that that we can say is that the value of an extensive property, and what's an extensive property? What does that word mean?
Depends on.
Intensives are independent.
So the extensive properties don't depend on the extent of the system. I don't think I got that backwards. Now you made me question my extensive properties. Okay, yes, these are extensive properties because they're not divided through by the mass. Okay. All right, so the extensive properties will be the weighted sum of each component. So this is similar to what we were doing for like some of the other values, like when we were determining the mass, the total mass, or the total number of moles, that it's the weighted sum of the individual components. So this is an extensive property. It does depend on the size or the extent of the system, but it's the mass multiplied by an intensive property. So we can add the weighted sum of each of these components together and find the total average internal energy, or the total average enthalpy for our system, which is a mixture of these individual components. We can also do it in the molar form. So if we're working in the molar form, and we use the number of moles times the molar form of internal energy, so it would be kilojoules per kilomole instead of kilojoules per kilogram. So be careful on units if you're doing that. The tables for ideal gases in the back of the book. Air is the only one that's in kilojoules per kilogram. All of the other gases are in kilojoules per kilomole. Okay, so a similar approach can be taken to determine the change in properties on a unit mass basis or on a unit molar basis. Okay, so we can find the sum of the individual components, but this time now we're using a mass fraction instead of the mass, and here we're using the molar fraction instead of the mass. So this looks like a lot of stuff, but it's really the same thing that we've been doing up until this point, that anytime you want to find this lump average, property value, or mass, or molar number, that you have to look at the weighted contribution of each of the individual components. And that weight is in the mass fraction form when you're dealing in units of mass, and is in the molar fraction form when you're dealing in units that have moles in them rather than kilograms, or in the English system, whatever it is there, pounds. And we can do this pretty easily for this internal energy and entropy and enthalpy, and we can even do the same thing when we're considering how to find an average specific heat for this system as well. So we can do it for the specific heat at constant volume and the specific heat at constant pressure, that we can add up the mole fraction multiplied by the individual contributions in order to determine some average specific heat. So it's all kind of the same thing. And if we're looking at ideal gas mixtures, all we need to know is the initial and final temperature for all of the property values except for entropy, because entropy depends upon the final pressure as well. So if we're determining the change in entropy for an individual component, we use this, this reference entropy, which again is tabulated in the back of the book, and it's in molar form for everything except for air. So you can imagine that this equation also has the universal gas constant and then lines over everything. It would be in the molar form. But now we use these mass fraction like pressures. So the pressure of this individual gas is equivalent to the mass fraction of the contribution from this individual gas multiplied by the pressure of the total mixture. So if you're given individual pressures of your gases, then you can just plug that in. But if you're given this mixture pressure and you need to figure out the pressure of your individual gas, then what they're saying is you can use the molar fraction to determine what pressure you should use when you put it into that equation as well. So this looks very similar to what we've seen already, but now we just have these mixture components in it that we didn't have before. Okay, so real gas mixtures, similar methodology, but now we find the gas in the ideal form. So a change in enthalpy, that should be, yeah, that's enthalpy also. So we can find the change in enthalpy, and then the change in internal energy is just the change in enthalpy minus this R correction factor using the table A15 to find our Z values. And then if we're looking at the table A29 and A30, then we find these Z correction factors for entropy and enthalpy as well. Okay. So we find, again, the ideal case, and then we use the correction factors to find our actual case. And the temperature that you use to determine the reduced pressure and temperature is the temperature and pressure of the mixture, not T sub I and P sub I. So when you're evaluating property values, use the temperature of the mixture to calculate your reduced pressure and your reduced temperature based on the critical points. So let's do an example of this, and this will be our last example for the day. It's another big, long 2-page one, but we'll do it. This time we only have two gases. It's 75% methane and 25% ethane by mass. Okay, notice that they give it. It's not by volume, it's by mass. So that means this time, instead of assuming 100 kilomoles, we'll just say, okay, we have 100 kilograms of it, 75 kilograms of of methane, and 25 kilograms of ethane. So if it's by mass, you have to assume 100 kilograms. If it's said by volume, then you could assume 100 kilomoles. And there's 2 million cubic feet of this mixture. Whew, that's a lot. Oh man, it's in feet. Dang it. Is trapped in a geological formation as natural gas at 300 Fahrenheit, 1300 psia. So it's down under the ground. And the natural gas is pumped 6,000 feet to the surface. At the surface, the gas pressure is 20 psia and the temperature is 200 degrees Fahrenheit. So we're going to use Hayes' rule and enthalpy departure charts to calculate the work required to pump the gas. Awesome. Okay, so now we go to table A1E, which is the English units, and we have to look up some of these properties. So we're going to look up the molar mass, C sub P, which comes from table A2, C sub P, T critical and P critical. So for methane, which is CH4, we have a molar mass of 16 pound mass per pound mole. C sub P is 0.532 BTUs per pound mass ranking. T critical is 343.9 ranking. P critical is 673 psia.
Will our mass need to be changed over to the English units? Or-
Yeah, so we wouldn't use 100 kilograms, we would use 100 pound mass. So instead of converting kilograms to 100 kilograms to pound mass, you just use that. Okay, just to make it easy, because it cancels out anyway, so it doesn't matter what it is. All right, and then our ethane, C2H6, is equal to 30, 0.427, 549.8, and 708 psia. And again, this is Rankine. This is pound mass per pound mole. Cannot read that, I apologize. Okay, so if we're assuming 100 pound mass, we can calculate our N is equal to the mass over the molar mass. So we have 75 pound mass divided by 16, and we have 25 pound mass divided by 30. So we find our N value for CH4 is 4.6875 pound moles And this is 0.8333 pound moles. 4.6875. So we can find the total molar mass of the mixture is these two numbers added together, 5.5208 pound mole. Now we can find our molar fractions. So for methane, which is CH4, is equal to the number of moles of CH4 divided by the total molar mass, or the total number of moles. So we get that 0.849, and the Y is C2H6 ethane is equal to 0.1509. Okay, I'm skipping a lot of steps. If you want to see it more thoroughly, look at the scan online. We can also find the total molar mass, which is equal to the mass of the mixture divided by the number of moles. So it's that 100 pound mass divided by the number of moles, which is 5.5208. So the molar mass of the mixture is equal to 18.11 pound mass per pound mole. And then we find an R value, which is RU over M sub M, is 0.1097 BTUs per pound mass Rankine. Okay, so we did all of that without even doing any equations. We just looked up these things and we start calculating our number of moles, total number of moles, mole fractions, molar mass, and our gas constant. Oh, we also want to get our CCP, which is equal to the mass fraction of the ethane times the CCP of the ethane. So it's the sum of the mass fractions of the individual components. So the mass fraction is 0.75 and 0.25. And we get that's equal to 0.506 BTUs per pound mass Rankine. Okay, so we have CCP, we have R, we have M, we have N, we have everything we need to figure this out. So, calculating the work required to pump this gas, how would we figure out what that is just symbolically? How much work is required to pump a gas up 6,000 feet? A lot. Okay. Yeah, thank you. So it's going to be a delta H plus a change in potential energy, right? And if we multiply that by the mass, then we'll get the total amount of work. Okay, so in this problem, we don't have time to go through it completely. We're going to find H2 minus H1 ideal. Then we're going to have to figure out this correction factor, ZH1 minus ZH2, to add it onto that. So we have to use K's rule, where we find the pseudo-critical point to determine a correction factor to calculate the mass. So just look at the example. I don't have time to explain. It won't do you any justice to listen to me explaining what I'm looking at on this paper. So look at the example online. You don't have anything nearly this complicated on the homework, but as we start moving into the other chapters, this type of stuff is what we will be using. Yes?
Did you say this stuff was going to be on the test?
Some of this is going to be on the test.
Okay,
It's not going to be complicated problems like this. It's going to be basic kind of stuff, seeing if you know how to calculate mole fractions and mass fractions and molar masses. So I may give on the homework, the type of problem that's on the homework will be similar to what you would have on the exam.
Will this carry over to the next exam?
Yes, it will carry over to the next exam.
How much of the partial differential stuff is going to be on there?
I'm not going to ask you to prove any of those equations, but you should know how to take a partial differential of an equation. Yes.
So you said it carries over to the next exam, and the next exam is final?
Yes. And it carries over because we're gonna be using this in all of the rest of the chapters. So I want you to have a basic understanding of how to do these molar mass and calculations. And if you've been in chemistry, this should be familiar, right? So, knowing how to do that is important, so that's what I want you to focus on for the exam. You can look through these examples later, but, this is the kind of stuff that in future chapters.
So, calm down.